other respect, I've been having some computer problems, and the IT people can't figure out what's going wrong. It may be a system problem, or it may be just my computer. Everything seems to be working fine, except when I go to enter attendance, it tells me that I'm on an unsecured system. Well, it's not an unsecured system. It says my certificate's out of date. It's not out of date, you know. They've checked everything. And so when I go to put attendance in, it either shuts down on me or enters on me, but then by the time I'm at the end and save it, I look at it and half of them are not there, even though I put them in. So it's just really bizarre. So that could be indicating there's some other problem somewhere, but I hope that won't be the case. Now, I wanted to wait till more people were here, but I don't want to wait until we're not. At first of the term, we were meeting down there in 255. And therefore, when we went over safety issues, we talked about everything from that room. And since today there is a chance, probably not a huge chance, but there is a chance we could have a weather situation today, I want you to know beforehand what we're supposed to do. We don't do the same thing we would down there, okay? And we don't have, I don't know why this room doesn't have, you can see one on that wall there? Map of the design of the room, okay. I didn't think it was back there, but anyway, it's not in here. You go out the door here. If you hear the alarm goes off, you're going to hear it before I will, because I'm hard to hear. So let me know. That's the weather alarm. So when we do have that, then you can take your stuff as much or as little as you'd like and go out orderly, not super slowly, but don't run, okay? Take it easy. Do it carefully. Go out the door here. Morning, come on in. Hang a right, okay? And the very next stairwell here is where we'll go down. Cameron's here. Okay. So we go down that stairwell just half a flight. Okay? Or I say just half a flight. My idea of the safest way to go was when you get off of there, you're going like you're going to the cafeteria bookstore. Just keep on going through those doors, but head toward the bookstore. Hang a left there toward the bookstore. Go through the bookstore. Don't stop. Okay? And then when you weave around past Student Financial Services, go out the door there. Then go, when you go out that door, hang a left, and then you'll do another right and go down to the lowest level. Now, if it looks like there's a backlog of students there, anywhere along the path there, you can stop, okay, because you're safe. Huh? Johnson, got it. Thank you. And it's Tiana, right? Okay. But if there's not a crowd there, go on down to the lowest level of the first floor, and then anywhere there, and we talked about that, everything from there on is like we said. Now, the reason I said go through the bookstore area, you're all interior there, okay? You're as interior as you can get in the building, so any of those spaces are pretty safe, okay? If you go down one more flight to the first floor there, then you are exposed to some glass at the doorways, okay? So I think it's better to go interior and down rather than go down and then get interior later, okay? So any questions about what to do if we hear that alarm? Now, since you're here to hear what to do, other people will be coming in. I don't want to go through this every time. So you sort of tell them, no, let's go here, yeah, because this is what he told us to do. Okay, there's that. Then the other thing, what's Tuesday? Election day, okay? And please make a plan to vote. What, less than 18? Okay. But please vote if you can. And that means planning, okay? See, I have class until 7:45 on Tuesday and Thursday. I can't possibly vote after class, so I have to make a plan to arrange to vote before I come to campus. Now, I don't think that'll put me late getting here, but in case I'm not here right at 8:30, Don't go anywhere. I will be here. It's just that hopefully there's going to be a huge crowd at voting. Everybody's going to be trying to vote at 7 o'clock, and it may be backlogged a little bit. But if that's not the case, I should be here with no problem, because I've got a full hour and a half to get voted and about 45 minutes to get here, so I should be able to get everything done in that time, hopefully. Okay, now, a few of you, before you left on Tuesday, looked at your test scores, and I know a few people were fairly disappointed. Let me say this, don't sweat that too much, because for most folks, this is going to be your lowest test score. I didn't want to say that before the first test, but the first chapter covers so much diverse material, and it's probably sort of new to you. I think most people, I've heard some people comment, second chapter seems to make a lot more sense, okay? It's a lot more focused. So I think you'll find your scores from now on will probably be heading up, certainly not the other way. So don't sweat it. You do get to drop the lowest test score. That could be it, okay? Now, any questions before we get going today? It looks like it's going to be a sparse crowd today, probably because of weather. Did any of the schools delay start, or cancel, or close? I didn't hear of any, so I thought we might have a more normal grouping this morning. Okay, if no questions, we are in 2.4, and remember, I'm not going to necessarily test you on this stuff. I hope there won't be any questions that pop up that you would need it, but I want you to be able to be familiar with it for in the future, whenever in the future you might need to run into complex numbers, and a few of you will at some point, then you will have been exposed to it. You heard it first here, okay? So we're on page 148. This is chapter 2, polynomial and rational functions. We're in complex numbers, which is in the polynomial part, though there can be some rational deals to do with it. And we had gone through adding and subtracting complex numbers. Well, what complex numbers were, standard form, that kind of stuff. Adding and subtracting complex numbers. And then we did multiplying complex numbers. And there was one very special case of multiplying two complex numbers with imaginary parts in them, and you didn't get a complex, well, it's complex, but no imaginary parts. What was that very special case? When you multiply the CC, complex conjugates together. What happens then? You get a real number. Now that's the key to dividing complex numbers. Okay? I want to do a flashback here. Okay? Now, I don't know, it may be a while, maybe ever, since you have done dividing by radicals. That wasn't a pretty sight, if anyone recalls that. In fact, division sometimes is a little tougher than the others. Okay? I want someone to give me, say, a mixed radical number. Part that's not a rational part. Give me a rational number, any rational number. 2, okay. Plus or minus? Plus. Now give me an irrational number. Okay, got it. Thank you. Okay. Give me an irrational number that has a radical to do with it. Anybody? Anybody? How about square root of 3? I thought I heard a 3 or something. Okay, so square root of 3. Okay, now let's divide that. Skylar I already have here. Okay, let's divide that by some other mixed rational number. Give me the same or different rational number. Anybody? Huh? 3. Plus or minus? Minus. And then another irrational number. Anybody? Square root of 2? Oh boy, very creative this morning, aren't we? Using all our numbers at our control. Okay. Now, if you think about writing this as a decimal number, the numerator would be sort of messy, right? But the denominator, just as messy, because see, square root of 2 is an irrational number, meaning it has no pattern, no way to write it as a ratio of two integers. It's just going to go on and on and on. So you just have to decide how many decimal places you want it to go on and on and on, okay? And then you take 3 and subtract that 1.414, blah, 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 however many away, and then you have to divide that into whatever that numerator is. Well, if you remember how to divide decimal numbers, let's just say that's going to be a 0.9, blah, 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 blah. Okay, whatever. I'm not sure it's a 9, but we'll do that. And it's going into 3 point blah, 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 blah. Okay, you like my blah, blahs, okay? To divide decimal numbers, you have to move this decimal as many places as you decided you wanted to take that number, and then you have to move that decimal place that many as well. And then you start your division. This is review of long division. Y'all have calculators, you probably never did long division. No, I'm just kidding, sort of. And then when you start dividing, you got to multiply. Where is it? There we go. Then you got to multiply whatever your quotient was there times all those digits. And that is a miserable mess. So there was an easier way to divide irrational numbers. Does anyone remember what it was? Jake, what did you say do before? Well, except not complex, multiply by the denominator's conjugate. What is the conjugate of that denominator? 3 plus the square root of 2. Okay? But if you multiply the denominator by that, you've got to multiply the numerator by that as well. Okay? This is a flashback. Hopefully you remember it. Okay? Now, why multiply by that? Let's FOIL this. 3 times 3 is 9. And 3 times root 2 is 3 root 2. Minus 3 root 2, 0. You lose the radical. And then root 2 times root 2. Oh, here's one. Okay. Were you absent Tuesday? Yeah, okay, I thought so. I thought, he's never absent. But when I had you mark that. Okay? Anyone figure out what root 2 times root 2 is? 2. Exactly. 9 minus 2, the denominator now becomes 7. And now, whatever that numerator became, I mean, it may be a mess, but it's a doable mess. That would be 6 plus 2 root 2 plus 3 root 3. Who picked these numbers anyway? Plus root 6. Whatever that is, you can write it as any long length of decimal as you can. And I can do 7 into whatever decimal. Let's see, what would that be? Let's just say it's 20-something. 20, blah, 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 point, blah, 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 blah. As many places as you want to put. And I can just do 7 into that, 7 into that. I can do it in my head. I don't have to have a calculator or anything else. It's much easier. So you see, we found dividing irrational numbers is much better. Do you remember what that process is called? Multiplying by the conjugate? It's called rationalizing the denominator. You make the denominator a rational number, 7, rather than some irrational number, 9 point blah blah or 0.9999, 9 point blah 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 blah. Okay, that's miserable to divide, especially back before they had calculators. So everybody always rationalizes denominators to make the division easier. Okay? Now, come back to the future. Okay? I think this is where we start today. To write the quotient of A plus BI and C plus DI in standard form, okay, where C and D are both not 0, okay, why could C and D both not be 0? Why do we prohibit that? Yeah, then you're dividing by 0. You can't do that. Ever, ever, not even with complex numbers, okay? So as long as C and D are both not 0, either one of them could be, but not both, then multiply the numerator and the denominator by, guess what? The conjugate, complex conjugate this time of the denominator. Because guess what that gives you? I would put parentheses around this. That gives you a real number. Every time. Multiply by the conjugate of the denominator. That gives you a real number. And then here is your real part, A times C. And this just happens to be another real part here. Plus BI times minus DI would be minus BDI squared. But I squared is -1. So that would be plus BD. This just happened to be that way here. That's your real part, and then your imaginary part of the numerator is going to be minus ADI plus BCI. So BCI minus AD. BC minus ADI. Real part, imaginary part, over a denominator that's real. So this over that is your real part. This over that is your imaginary part, which they're going to proceed to do in the next step. Okay? No, they didn't. Okay, I thought they would. All right. I hate it when they do the problem for you, but they've already started. Let's just back off. Let's clear this. Okay. Let's do example 4. 2 plus 3i divided by 4 minus 2i. How would you do that division? Can anyone divide by the square root of -1? I can't. Okay. Don't even try it. So I surely can't divide by -2 times the square root of -1, or 4 minus 2 times the square root of -1. So what would you do? Complex conjugate, which would be 4 plus 2i. But if you multiply the denominator by that, what had you better do? Numerator by 4 plus 2i. Okay. I have very rarely, but occasionally seen someone multiply the numerator by its conjugate. No, that's not what we're doing. You multiply the numerator and denominator by the same thing. Okay? Because that's equal to 1. All right? Where do you want to start? Numerator or denominator? I don't care. Denominator. Okay, what does that denominator become? You can probably do it in your head, but if not, work it out. Second? I don't think so. Okay, good. All right. Good morning, Vietnam. Okay. 16. Second? Plus 4, you said? Okay, good. Plus 4. That's going to be a 20 in the denominator, a nice, real number. Okay? Now you put off the hard work. Let's do the numerator. That starts with a... Now it's going to be a. That's where you were looking before, wasn't it? Okay. Then you're going to do... Second? Or you want to go on and do the other one? I don't care. What you want to do? That one? Okay, what's that going to be? Plus 4i. Next. Next. Plus 12i. And last. What's that? 6i squared plus 6i squared. Okay, but now you have to answer the next question. What in the world is I squared? Negative 1. So that makes that a negative 6. So 8 minus 6 is 2. There's the real part over 20 that we can now change later. And then we're going to have a plus. And what's the imaginary part? 16 over 20 times I. Right? Now, don't leave it like that, because we can reduce. What would that be? Anybody? 1/10 is what I heard. Plus 4/5 I. There it is in standard form. Real part, 1/10. Imaginary part, 4/5 I. Make sense? Did you really want to go back and try dividing by 4 minus 2i? Please say no. Okay. I would say you can't even do it, okay? But this way it comes out pretty simple. All right. Now, let's go back and see how they did it. Whoops. Yeah. So here's their example 4. They start by multiplying numerator and denominator by the conjugate of the complex conjugate of the denominator. And I would definitely, folks, put in parentheses here. Why do you reckon I say that? Yeah, you're going to wind up foiling, but if you don't put those parentheses in, it looks like the 3i is multiplied by that, not the 2. When you group them together, you know the whole entity has to be multiplied by that. You know it's got to be done here, but you may forget about it up here. So I highly recommend putting your parentheses in both numerator and denominator there. Okay? And then they did the math just like you did. 8 plus 4i plus 12i plus 6i squared over, and they just did they wrote it out, 16 minus 4i squared. Okay? But we can now figure out what I squared is, negative 1. So the 6i squared plus 6i squared becomes negative 6. So that's why it moved over with the 8. Combine like terms, you might think of them, the I terms, and they become 16i. And in the denominator, the minus 4i squared becomes a plus 4. Okay, because I squared is negative 1. So that gives us 2 plus 16i over 20. Okay? Don't leave it like that. Okay? Take it a little bit further. 2 over 20, 1/10, plus 16 over 20, 4/5 I. Okay? That's in standard form. The other form is sort of okay, but you still can reduce it. Okay? And we'll see instances where that other form sometimes is how we leave it. The book never does. Okay. There is a checkpoint after example 4, so please do that. Any questions on dividing complex numbers? I wasn't going to do this much, but I am. So, I'm going to try to get through this faster. Complex solutions of quadratic equations. Now, if you ever run into, and you will, okay, I'll try not to make you have it in this class, but at some point, you could have a number that's something like the square root of negative 3, which you know in the real number system you can't do. But in the complex number system you can. So what you do to that is factor out of that negative 3, factor out a negative 1. Okay? So that becomes the square root of negative 3 becomes the square root of 3 times negative 1. Okay? Then break that radical into 2 pieces, square root of 3 times the square root of negative 1. And what's the square root of negative 1? I. Now, they like to write it this way. Plus square root of 3i. I don't like to write it that way. Can anyone guess of why I don't like to write it that way? Just because I'm being obstinate? Maybe, but here's the real reason. What if this line just accidentally scooted over a little bit? Now it looks like the I is under there, okay? Or even if it didn't, you might read it that way. So I always like to do I root 3. I know that's not standard form, but it removes the ambiguity of whether that's I under the radical or not under the radical. So to me, if I can make it clearer, and have I told you what we used to say in the Navy? You try to make things sailor-proof. So not even a sailor can screw it up, you know. But, so I try to make things student-proof. Okay, never mind. Oh, I wouldn't say that, would I? Okay. Not even a student-proof. That's it. Okay. So the number square root of 3i is called the principal square root of -3 because it's the positive one. So the principal square root of a negative number, when a is a positive real number, the principal square root of -a is defined as square root of ai. But I would say I times the square root of a, just to make it clear the I is not under the radical. Okay? Any questions? All right. Now, if you were asked to solve this, how would you proceed? I hear the wheels turning. Let's see if we can factor it, okay? Let's see. What's the only possible factorization of 3x squared? 3x times x, okay? Then we look where? Sign of the last term is plus. That means these two signs have to be? Nope. The same. To give you a plus there, they have to be the same, right? Minus times minus is plus, and plus times plus is plus. So they have to be the same. What sign do they have to be then? Negative. Both negative. And what's the only possible factorization of 5? 5 and 1. Let's try it. Okay? Let's FOIL it and see what we get. 3x squared? Yes, yes, yes. That's exactly what I wanted. And then we get a minus 3x minus 5x. That gives us minus 8x. Not going to work. Wrong number. Right sign, but wrong number. So let's change the numbers. Okay? And you only got one way to change them, too. Change that to a 1, that to a 5. Okay? Let's see if that will work. 1 and 5. Now what do we have? Minus 15x minus x. Minus 16x. Even worse, okay? You're not going to get there. It's not going to factor, is it? And if it's not factorable, what do we do? Throw up our hands and quit. No, we would never do that. Okay? Minus, huh? Second. Alexis, I thought that's who you were, but wanted not to call you by the wrong name. Okay. So what do you say? Quadratic formula. How does that go, by the way? X is equal to minus b plus or minus the square root of b squared minus 4ac all divided by 2a. And that c is under the radical. So that's what I do to make sure I covered enough. What in the world are your a, b, and c? Where did that come from? Say again? A little louder. Okay, 3 is A, -2 is B, and 5 is C. Okay, now we just plug in the numbers and we have an answer, don't we? Ooh, let's not do that. Okay, so what would your first be? 2 plus or minus the square root of, which is 4 minus 4 times, what's your A? 3. What's your C? 5. Okay. All under, and then divided by 2. What's your A? 3. Okay. So that's going to be 2 plus or minus the square root of 4. Okay. Here's where I stop, pause for a moment, and count my negative signs. Okay? This minus 4 is always, that's always a minus sign there. But these two are both plus, so I only have one minus sign. What does that make this sign? Negative. Right? If you have one minus sign, it's going to be negative. Two minus signs, it's going to be positive. Three minus signs, negative. Okay? Those are your three chances. It's either going to be negative, positive, or negative. Count the minus signs and that'll tell you. Okay? So this is going to be negative. Okay? So minus, and then what's 4 times 5 times 3? 60 over 6. Okay? I'm going to come back here for a bit. That's 2 plus or minus the square root of what? Negative 56 divided by 6. Warning, bells going off, whistles, red flags all over the place. The real number system, we can't take the square root of negative 56. But in the complex number system, we can. Okay? So that's going to be 2 plus or minus the square root of. First thing I'm going to pull out is my minus sign, minus 1. Now, the next that I want to pull out, are there any perfect squares hiding in 56? Anybody? Perfect squares in 56. 4 times what? 16? Yeah, 4 times 6. Is that right? No, that's not right. 4 times what? 14. Yeah, 4 times 14. So then you could pull out a 4 and pull out a 14. Is that legal in most states? Okay. And we're going to divide all that by 6. Okay. So that's 2 plus or minus. What's the square root of 4? 2. Square root of negative 1? I. And square root of 14 is square root of 14. You can't do anything with that. Over 6. Now what do you notice you can do? Factor out a 2 in the numerator. That's 2 times 1 plus or minus I root 14. That goes through Sylacauga, doesn't it? No, I'm just kidding. Over 6. But 2 will go into 6 3 times. So in standard form, that's 1/3. There's the real part. Plus or minus, and however you want to do it. If you want to write it, root 14/3 times I. That's pretty clear that it's not, the I isn't under the radical. But if you like to put the I in front, I root 14 over 3. That's how I probably would do it, but that's perfectly fine. Two solutions, but we had a quadratic, right? But they're both complex. Well, all roots are complex. These are non-real. They have imaginary components. Okay? And this is Alexius. Okay. Has anyone else snuck in while I wasn't looking? Okay. Now, that's where you wind up needing imaginary roots. Okay? Because when you wind up with a negative number in that radical, when you're having to do quadratic formula, that's where the i's come to play. I'm going to try to avoid those on your tests and quizzes and stuff. Or you won't have a quiz on this, just a test. But if I do screw up and get one in there, you'll know how to handle it. Okay, so let me erase all this. I wasn't going to do all that, but I thought since it's here, I'll go on and do. Oh, I'm sorry. Did you have it all? Okay. Okay. Did I erase too soon? Anybody? Well, they're going to show you how to do it. Here's the quadratic formula, just like we did. Came up with the same thing we did. Factored out a 2, and I just don't like that I right after the square root there, but they do it, okay? And then that simplifies to be 1/3 plus or minus root 14 over 3 times I. That's clearer that way, that the root 14 over 3 is not, the I is not under the radical, Okay, that one up there, I could be mistaken, you know, easily fooled. Okay, that's the last, I can't believe this, that's the last slide in the section. Okay, in fact, I can't even see. Oh, I see what happened. I skipped example 5. They skipped it, and I did too. Because I'm not going to ask you any of those, please do those on your own. And if you have any questions, ask. Do example 5, do its checkpoint, and do the checkpoint for example 6. All right, let's do the vocabulary. A blank number has the form a plus bi, where a is not equal to 0 and b is equal to 0. A blank number, okay, it is a complex number, but all numbers are complex numbers. This one, the b is equal to 0, so what's that? If b is equal to 0, that is a more specific than complex. Because b is the imaginary part. So if a is all you got, it's a real number. You see that? All right. Number 2. And blank number has the form a plus bi, where a is not equal to 0 and b is not equal to 0. The only reason I know what answer they want is because they put the an in front. They're calling that an imaginary number. And that would be the case. I would prefer calling it a complex number with an imaginary part, but that's too many words. Number 3, a blank blank number has the form a plus bi, where a is equal to 0 and b is not equal to 0. Pure imaginary number, okay, with no real part, okay? Number 4, the imaginary unit I is defined as I is equal to square root of -1, and where I squared is -1. Perfect. Number 5, when a is a positive real number, the blank blank root of negative a is defined as the square root of, there they gave it, didn't they? Or part of it anyway. The square root of negative a is equal to square root of a times I. I already said what the second blank is. Principal square root, perfect. And number 6. The numbers a plus bi and a minus bi are called blank blank. Second. Complex conjugates of each other, and their product is the real number a squared plus b squared. Okay. Now you don't have to do any of these if you don't want to. That's completely up to you whether you do any of these exercises. Okay. The odd ones are there. All the odd ones are at calcchat.com. The red letter numbers are at calcview.com. So you decide whether you want to do any of those or not. Now we get to the real heart of this portion of the chapter. Okay. Everything's been leading up to this, finding the zeros of polynomial functions. This is the last section strictly on polynomials. Okay. And I don't know why that did that, but I'll open it again. All right, 2.5. Well, maybe I'll open it. Grind, grind, grind. There we go. Any questions so far? Isn't it fun watching little dots move across the page? I don't know what its problem is. It sure is taking a long time. I don't like PowerPoint. It's a handy tool, but it's just not my favorite. Yes, it is. Okay. And this is a fairly long section here, too. Okay, so we're still in Chapter 2, Polynomial and Rational Functions. 2.5 are zeros of polynomial functions. Now, we've already been dealing with zeros of polynomial functions, especially when we could factor them. Okay? So we'll use the fundamental theorem of algebra. We'll first talk about what that is to determine the number of zeros of polynomial functions. We've already talked about that some. We gave the maximum number you can have. Now we'll talk about how many you really can have. We'll find the rational numbers of polynomial functions. That's going to be a new test, and it's really pretty powerful. And then we'll find complex pairs of complex zeros. We'll just sort of skim over that because I'm not going to test you on complex. And then we'll find zeros of polynomials by factoring, however we can. Then we'll use Descartes' rule of signs and the upper and lower bound rules to find other clues on what the zeros of polynomials are. And finally, we'll find zeros of polynomial in some real-life applications. We can't wait. Okay. Now, let's start with the fundamental theorem of algebra. Okay? Now, everything up till now, or up till Tuesday, I'll say, we were dealing only with real numbers. Once we introduced complex numbers last Tuesday and finished with them today, or continued with them today, now we're dealing with the complex number system. And in the complex number system, every nth degree polynomial function has precisely n roots, n zeros. Okay? Before we said up to n zeros, but it didn't have to have n. Now we say it has to have precisely n zeros. That important result is derived from the fundamental theorem of algebra, first proved by one of the incredible mathematicians, a German mathematician called Friedrich Gauss. Okay? He wasn't just a mathematician, he was quite a scientist as well. Does anyone know the unit for magnetic field? There are actually two of them. Anyone know? Gauss was the old one. Tesla is the new one. Okay? And they related to each other, of course, too. Okay? Gauss probably was one of the most prolific writers of mathematics we've ever seen on the planet. Okay? Had a pretty good long life there. What was that, about 78 years or something like that? If my math is right, I believe it is. Okay? And the fundamental theorem of algebra says if f is a polynomial of degree n, of course n has to be greater than 0, then f has at least one zero in the complex number system. But remember, folks, what's the complex number system? All real numbers and all imaginary numbers. It's both of them. Well, that's a pretty lame theorem, okay, that it has at least one. We just said it has precisely n. Well, Gauss took this and moved on with it, okay? So using the fundamental theorem of algebra and the equivalence of zeros and factors, you obtain the linear factorization theorem, and this is then the more specific one, and the one we'll be using. If f is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors. Okay, so this f of x may have some number a sub n that you factor out from. It may or may not. That could be 1, it could be anything. Okay? But it's usually a real number. Okay? But then you have times x minus c1, times x minus c2, times x minus c3, times x minus, all the way up to x minus c sub n. Whatever that n was. Fifth degree polynomial, you have 5 factors. If it's a first degree polynomial, you just have the 1 factor. Okay? Those ci's, C2, C3, up to Cn, those are all complex numbers. But remember, all real numbers are complex numbers too. So that could be a 7, a 14, a minus 3, 4/3, you know, pi halves. It could be any of those numbers, or it could be 7 plus 3i. Okay, it could be any imaginary or real number. Okay, that's what Gauss's thing. Now, guess what? If those are factors, then x equals c1 would be a solution, a root, a 0. Okay, and if x equals c2 would be 1, x equals 3 c3. So we're right back to where we started. We have exactly n factors, so we have exactly n roots. Now, remember, some of those may be repeated. If that was x minus 7 and the brother x minus 7, yeah, both of those are roots. It would be a double root. So you can have multiple roots there. Now, note that the fundamental theorem of algebra and the linear factorization theorem tell you only that the zeros or factors of a polynomial exist, but guess what? It doesn't tell you how to find them. That's going to be what we do the rest of this section. Those theorems are called existence theorem. Yay, we know they're there, but how in the world do we discover them? That's going to be our task from now on. All right. So, first degree polynomial. F of x equals x minus 2. This isn't much of an example, is it? It has exactly one root. What would that be, or 1, 0? What would it be? X equal 2. Because x equal 2 makes that equal to 0. Okay? Pretty straightforward. All right. Counting multiplicity, how many zeros do you think this one has? It has 2 complex zeros. Okay? Now, let's see what they are. What would you do to determine that? Let me get my pen back. It's what? Factor. And how does that factor? You've already been here. Okay. How does that factor? Anybody?
It does have to be
negative. Negative. Perfect. Oh, and Dimitri decided to show today. Good. There you are. All right.
1 and 9.
Second. You could have a 1 and a 9. Let's see if that works. I don't think so either. That would add to minus 10x. Both threes. Okay. That counting multiplicity should have given that away. If you put both threes there, it does work. So what's your 0?
Plus minus.
X equal, say again? Yes, x equal 3 or x equal 3. Okay. Now, those are 2 zeros. They're the same number, but that's a multiplicity of 2. So we do count those as 2 zeros. Okay? Because they were each a factor. Okay? So, yep, x minus 3 times x minus 3 has exactly 2 zeros. They just happen to be the same number. It's called a repeated 0, or a multiplicity of 2. Okay, how about this one? How many zeros does that have? It has 2 also. No, how many?
Oh, I said
3. It has 3, okay? I was looking at it, thought, okay. Did anyone figure out what maybe they are? What would be the first thing you do? Second? Help me. Factor out an x, and that leaves you x squared plus 4. Okay? I can't factor that x squared plus 4 any further unless I use complex numbers, imaginary numbers. And sure enough, you would. It's x plus 2i, x minus 2i times x plus 2i. That would give you that. Okay? But those are complex zeros, but it still has them. X equals 0, that's 1, and then the other 2 are complex. Okay? So it does have exactly 3 complex zeros. Only one real zero, but 2 that have imaginary components. Okay? And they do it in the book. I'm sort of going to glaze over those. There's a checkpoint there. Please do the checkpoint. All right, let's show how they do it. I'll let you see them do it, even though I won't do it myself. Okay. Yep, they factored out the x, gave you x squared plus 4, and then they saw you can't factor that with real numbers, but you can with complex numbers. Okay? And again, don't sweat these, but just know you can do it. So the 3 zeros, x equals 0, that's the real one. X equal 2i, that's one of the complex ones. And x equal minus 2i, that's the second complex. Okay? Now, I'm going to jump ahead a little bit. As long as your polynomial has real coefficients, no complex coefficients, real coefficients, then if you do have a complex solution with an imaginary part, guess what? They're always complex conjugates. There's always 2, and they're complex conjugates of each other. Okay? If it does have a complex solution, one with an imaginary part, they're always going to show up as complex conjugate pairs every time. And this, is that a complex conjugate? Are those complex conjugates of each other? Yes. 0 plus 2i and 0 minus 2i. Yeah, they surely are. So anytime you have real coefficients, if you do have any imaginary parts, they will be in pairs, conjugate pairs, complex conjugate pairs. So let's get back to real numbers, and more specifically, rational numbers. Someone remind me, what's a rational number? Don't give me anything to do with gender, that's out of the question, okay? What? Rational number. What's the first 5 letters in rational? Ratio. So that's a ratio of 2 integers as long as this bottom one is not 0. You can never divide by 0. So we're going to do the rational zero test. Now this is a little bizarre at first, but it turns out being really, really powerful. The rational zero test relates to possible rational zeros, possible now, okay? Rational zeros of a polynomial having integer coefficients, okay? Before I said you need real coefficients, now you need integral coefficients, which is most of the time what we've got, to the leading coefficient and to the constant term of the polynomial. So here's the rational zeros test. If the polynomial f of x is equal to a sub n, that's just the coefficient of this term, times x to the n, plus a sub n minus 1, just the coefficient for the n minus first term, times x to the n minus 1, plus, and you count down until you finally get to a sub 2, x2, plus a sub 1, x to the first, which is just x, plus a sub 0 times x to 0, which is just 1. That is your polynomial, okay? Excuse me. Standard form for the polynomial. Decreasing order of your powers. Okay. Here's what your rational zeros test does. You take all your rational zeros, all your rational zeros will be of the form p over q, where p is an integer, q is a non-zero integer. Now, p and q have no common factors other than 1, of course, okay? And p, where do we get the p? All the possible factors of that a sub 0, okay? Q, what's it? All the possible factors of your a sub n. Your leading coefficient for the denominator, your constant term for the numerator. Those are going to be your possible rational zeros. You can't have them any other way, okay, except that. Okay? Now that's going to usually give you way more than are possible, but at least those are all the ones that are possible. Okay? So to use that rational zero test, you should first list all the rational numbers whose numerators are factors of the last term. And here's Ashley. Did you say something? Yeah, sorry about that. And it could get worse. Okay. They say most of the worst stuff is going to be further south of us, but we still could have some bad here. Now, since we got probably most of you here now, I don't have my watch out. Let me see how we're doing. Okay. Let me go over what I said earlier, because a lot of you weren't here then. When we had our safety stuff at the very first of the term, we were down in that room, 255. Since then, we've moved here, and I didn't go back over what our evacuation routes would be. Okay? If we were to hear the siren go off today, and if you're in this classroom, what you do is go out into the hall, hang a right, go to that first stairwell, which is just down the hall here. Go right down the stairwell, and just go down that first level. Then go through those double doors like you're going to the cafeteria or the bookstore. Only hang a left and go to the bookstore. Go through the bookstore, okay? The reason I'm taking you this way, once you get down that half flight of stairs there, you're all in the interior part of the building. That's the safest place to be if we had inclement weather, okay? You don't want to be on the outside. That's why I didn't say go down all the way to the first floor and then go around, because there you're exposed to glass doors and things like that. So if you go in, you're interior. So go through the bookstore part, then go past financial aid office and stuff, and right past financial aid, there's a double doors. Take a left there and turn and go into the old part of the hallway. It's a lot like this part. And then when you go through into that old part, hang a left, then hang a right, go down one more flight. That's where we wound up in our other class, okay? And then you're on the lowest level. And stay interior. The restrooms would be interior. You might not want to spend a few hours there, but you could. The hallway is good. The dean's office is okay, academic dean's office, if anyone's there. Don't break in, but if anyone's there, that would be okay. The classroom that's there, the developmental classroom, math classroom, that's not bad. It's sort of a big space, so stay near the interior wall. That would be the safest place. Any of the corners or walls would be next. Out in the middle is not as safe, okay? And then the first room in the library, which is on the right, is the computer room. That's a good safe room. And the next room on the right, that's pretty safe as well. Don't go any further into the library, because then you're on the exterior part. And here's Ryan. All right. Anyone who comes in later, follow the rest of them, because they've heard it, some of them twice now. So here's what the rational zeros test is. First, list all the rational numbers whose numerators are factors of the constant term, a sub 0, whose denominators are factors of the leading coefficient. So these are your possible rational zeros. All the possible factors of the constant term divided by all the possible factors of the leading coefficient. Now, having formed that list of possible rational zeros, then they say use a trial and error method to determine which, if any, of the actual zeros are the polynomial. Let me give you a hint on what to use in that trial and error. Basically, synthetic division. Works like a charm. Okay? Note that when the leading coefficient is a 1 and only a 1, then your denominator is only 1. So all your factors are integers. Okay? The rational zeros are simply factors of the constant term, which would be integers. So here's the problem. Find the rational zeros of f of x is equal to x to the fourth minus x cubed plus x squared minus 3x minus 6. Okay? Now, number one, I can't factor that. Number one, it's a 5-term polynomial. If it was even number of terms, I might be able to do grouping, but not with odd terms, odd number of terms. There's no way I have to factor that. Okay? So we go to the rational zeros test. And what's the rational zeros? They're going to be of the form P over Q, where P is what? All the possible factors of constant term. So what are those possible factors? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. That's all the possible factors of that constant term. Okay? Divided by all the possible factor of your leading term. What's your leading term? Or leading coefficient? 1. So the only possible factors there, plus or minus 1. Okay? This is pretty easy. Here are your possible rational zeros, plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 4. Okay. Now, I'm going to give you a really handy hint. The easiest one, you tell me, what do you think the easiest one to test will be? Just make a guess. Of those possible factors, there's 8 possible factors there. Which one's going to be the easiest to test? 1. Okay? And here's how you do it. Okay? If you plug the 1 into that, now we're not going to do that for all of them, but if you plug the 1 in, this would be 1. This would be minus 1. That would be 1. This would be minus 3. That would be, guess what? Add your coefficients. That's all you do. Because everything's going to be a 1 if you use plus 1. So this would be 1 minus 1. That would be 0. Plus 1, you're back at plus 1 again. Minus 9, minus 8. Not a 0. Yes?
So how did you get those numbers on the top?
On the top. You take the constant term and list all the possible factors of 6.
Okay.
Okay? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Okay? Then for the bottom one, your leading coefficient. Plus or minus 1. That's all. Yes?
Where'd you get that 4 at?
I don't know. I think you told me to write it there and then you messed up. Why did you do that? Okay? That's a 6. Okay? I was just carried away with numbers. Okay? Plus or minus 6. Making fun of me now, aren't you? Okay? All right. Good deal. Thank you. All right. So we tested 1. It's not a 0 because that doesn't add to 0. Now, the rest of them, the easiest way to test is synthetic division. Okay? Because remember, if your remainder comes out as 0, it's a factor. It's a 0, right? So let's do minus 1. Nothing special about minus 1. So what do you put down after the minus 1? Oh, it's been so long. At least it's a couple of days. Synthetic division. What do you write down? Help me, people. Somebody. 1. Minus 1. 1. Minus 3. Minus 6. Do we have enough numbers there? How many we got? 5. What's your maximum exponent? 4. Yes, it always has to be one more. And then we skip a line, draw a line. And then you bring down the 1. You tell me the rest of them. Negative 1. Negative 2. 2. 3. Negative 3. Second. Negative 6. What? 6. 0. Ding, ding, ding. We have a winner, folks. Okay? X equals negative 1 is a 0 of that polynomial. Right? Okay. So we found one of your rational zeros. X equals negative 1. Okay. Now, to find the next one, guess what? You could have repeated zeros. So we're going to have to try negative 1 again, just to see if it's a repeated 0. And what you do, skip a line, draw a line, bring down the 1, negative 1, negative 3, 3, 6, negative 6, negative 12. Nah, not 1. Looks so close, but it's not going to make it. Okay, so we erase those. That's easier for me to do than you, but I can do it. Okay. And we'll also erase that. Okay, and it's up to you what you want to try next. Positive 2, let's do it. I already brought down the 1. What will be next? 2. Second. 0. 0. 3. 6. 0. Ding, ding, ding. We have another winner, okay? X equal 2. So x equal negative 1, x equal 2. Okay? Do we continue? No, because we wound up with 3 as your quotient. 3 digits as the quotient. What does that represent? A quadratic. And we can do quadratics. That would represent x squared plus 3. Set it equal to 0 to find their zeros, and guess what you're going to get? 2 complex zeros. X equal root 3i and minus root 3i. Okay? Second? I can't hear you.
Where'd you get 3?
Where did I get 3? Okay? When we're doing our synthetic division, did you agree this was 3? Right? Then what this represents, remember, this started off being our x to the 4th. We divide once, it becomes x cubed. We divide again, it becomes x squared. So x squared plus 0x plus 3. Those are our coefficients of your polynomial. You drop 1 degree every time you divide, because you're dividing x plus 1 into that. And you come up with x to the 3rd power. Do x minus 2 into that, you come up with x to the 2nd power. So this is your coefficient of the square term. Linear term is a 0. Constant term is a 3. Got it. Now, zeros for that, not real. Complex. Now, going to suggest something to you. On the test I will give you, if I do it right, it's going to say find all the real zeros. This would be the answer. The other 2 zeros, you know there's got to be 2 more. They're going to be complex, and they're going to be complex conjugates of each other. So the other 2 would be I root 3 and minus I root 3. I like to write it that way. The book writes it the other way. You don't have to go that far, but that's what the last ones would be. Now, if I said, what's the complete factorization of this polynomial, we could do that. Because what would be the factors? If x equal minus 1 is a 0, what would be your factor? Oh, we're out of time, aren't we? Oh, I'm so sorry. Okay. I was getting carried away. Okay. You know, I just skipped example 2. We're going to start next time with example 2. Sorry about that. I didn't notice that. We'll start with example 2, and then we'll go on.
Why'd you pull the imaginary from?
Well, I was just showing that those are 2 complex zeros. Okay? Your fundamental theorem of algebra and the other things, linear factorization theorem, says you're going to have 4 complex zeros. We only found 2 real ones. The other 2 have to be imaginary. Is that what you're asking?
Yeah, exactly.
Okay. All right.
Crazy, bro.
So, all right. See you this afternoon. All right.